All right, guys, so today we're going to talk about L'Hopital's rule. So what is L'Hopital's rule good for? So let's say that we're going to compute a limit. Let's start with the limit as x goes to 1 of e to the x minus 1 all over the cosine of pi x plus 1. And the way we did it before is we started by evaluating our function that we want to compute the limit of at the x value that the x is going to be tending to. So x at 1. So we're going to evaluate this function at x equals to 1. So let's do that. At x equals to 1, our function becomes what? Well, it becomes e to the 1 minus 1 over the cosine of pi times 1 plus 1. And so e to the 1 minus 1 is e to the 0 minus 1 over the cosine of pi plus 1. But cosine of pi is negative 1. You see already there's a problem. E to the 0 is also 1. And so you have 0 over 0. So what we said before was that we wanted to factor. And we wrote it like that. We want to factor. Remember? But whenever we try to factor this out, then we do say this, because we don't know how to factor that. And that is when you need L'Hopital's rule to compute the limit. So what does L'Hopital's rule tells you? So I'm going to erase my eyesight and I'm going to write the theorem here so we can apply it over here. All right, so let's write down the theorem. So if f and g are real valued functions on an interval that contains a point C, and the limit as x goes to C of f of x is 0, the limit as x goes to C of g of x is also 0. Moreover, if the functions f and g are differentiable at x equals to C, I'm going to leave that alone because I don't want to write it. If you have these two situations, what we're going to have is, so whatever is written needs still to have the derivative, the differentiability part. But what I need you to see is this, that the limit as x goes to C of C, let's erase well, to C of f of x over g of x is going to be equal to the limit as x goes to the same C of the derivatives. This is not a quotient rule. Be careful. That's a thing that people make a mistake with. You're taking the derivative of the numerator and the derivative of the denominator. So here we have 0 over 0, as this would give us what the theorem requires. So we can take the limit by taking the limit of the derivatives. And you say, well, how is that going to help? Well, often it is the case that when you take the derivative, so here you're going to be taking the derivative of your exponential, which is going to be x minus 1 e to the x minus 1, x minus 1 prime is the derivative of the exponential, is copy the exponential times the derivative of the exponent. That's chain rule. And then the derivative of the cosine is negative sine, but it's going to be a pi as well, of pi x. And this pi comes from the derivative of the inside. So derivative of the cosine is negative sine, evaluated at pi over x, or pi x, sorry, and then multiply times the derivative of pi x, which is going to be a pi. The derivative of minus 1 and plus 1, those two are 0, so I didn't write them there. All right, you say, you start with something that looked ugly and you made it even uglier. Well, let's take the derivative further and let's go ahead or finish that derivative and let's see if it's really that ugly. It's not going to be. So derivative of that is 1, so I get e to x minus 1 over the negative pi sine of pi x. All right, so I evaluated now, as an aside, evaluated at x equals to 1. And this one right here, I'm going to write it here. When I evaluate at x equals to 1, what do I get? Well, I get e to the 1 minus 1, e to the 0, over negative pi sine of pi x. And when I evaluate at x equals to 1, I forgot, sorry, I didn't put x equals to 1. So I evaluated at x equals to 1, I get that this is going to be e to the 0, which is 1, over negative pi times the sine of pi, that's 0. So this form right here tells me that this limit now diverges. It's going to either go to positive or negative infinity. So in this case, by the way, if you're going to pi, you draw the sign. You're going to have to be careful whether you're going from the positive or the negative, because this one is always going to be 1. So this will change signs, because the sign, remember, is going to give you a graph that looks like this. And as you're approaching pi, from the left is going to be on the positive side, from the right is going to be from the negative. So it will depend on what side of the limit you're going, whether you get positive or negative infinity. All right, so the first example, L'Hopital's rule allows us to determine that the limit diverges. Let's do one where it actually converges. So let me write down an example where it converges. Okay, so let's write an example where the limit will converge. We're going to use L'Hopital's. So let's do a typical one. So limit as x goes to 1 of the square root of x minus 1 over x minus 1. Something very straightforward. All right, so here, as x goes to 1, let's do our little aside here. When x is equal to 1, we will do that this takes the value of the square root of 1 minus 1 over 1 minus 1, and that gives us 0 over 0. So we are in this situation, 0 over 0. That's important that we get that. We cannot just apply L'Hopital's if it's not 0 over 0. So in this case, we can. And the limit would be limit as x goes to 1 of derivative of the square root of x is going to be 1 over 2 square root of x. You get that by writing the square root of x as x to 1/2, taking your derivative. You end up with this. I'll save you the trouble. Derivative of x minus 1 is going to be 1. So now you can evaluate it, and it's going to be 1 over 2 times 1 over 1. That over 1 does nothing. It's just going to be 1 over 2 times 1, which is 1 over 2, which is also known as 1/2. So we get that limit very, very easily. Remember, how did we do it back at the beginning of the semester, or actually in Calc 1, depending on which class you're in? Well, the way we did it, is by multiplying both sides of this by the square root of x plus 1 over square root of x plus 1. Then we would do all the algebra and end up with the same limit. So L'Hopital's rule is a lot faster. Let's do one more. So let's take a look at this limit. The limit as x goes to 0 of, let's do the cosine of, oh, that's a bad one. Well, let's write now this one. Cosine of x minus 1 over x. Let's do that one. All right, so with that one, if you evaluate it directly, this is a typical one that we did, that we just took as truth. If you evaluate it, you get cosine of 0, which is 1, minus 1, that's 0 in the numerator. Then when you evaluate at 0 here, you get 0. So 0 over 0, I can use L'Hopital's. So then when I compute my limit, I get the limit as x goes to 0. Take the derivative of the numerator. Derivative of cosine is negative sine. And then the derivative of x, derivative of minus 1 is 0, so I don't add it. And derivative of x is 1. So I evaluate the sine of x at 0, and I get the sine at 0, or negative sine at 0, which happens to be 0. But we already knew that limit. But you see how we can compute it once we know L'Hopital's rule. Let me erase, and I'm going to move on to a second version of L'Hopital's rule, which is what I was thinking before writing this limit. So let's go ahead and look at the second version of it. All right, so the next version of L'Hopital's rule, you see I didn't erase much. I still will need the differentiability. But the limit as x goes to c, now I'm going to assume is either plus or minus infinity. And the same for this one, either plus or minus infinity. If I have that, I can apply the theorem and it works in the exact same way. So let's do an example real quick. I want to do one that usually is done in a different setting, but let's think about this. Limit as x goes to 0 from the right. And by the way, this can be one-sided limits as well, as evidenced by my example, of the natural log of x over 1 over x. Usually that one would be stated as the limit as x goes to 0 of x times natural log of x. You notice that these two quantities are the same because multiplying times x is the same as dividing by its reciprocal. But in this form, it's important because if I evaluate it here in this form, I'm going to have that's going to be the natural log at 0, which is undefined, but at x equals, as you approach 0 from the right, remember the graph of the natural log real quick, has an asymptote at x equals 0. So it's going down to negative infinity. So this limit right here of what I called f would be negative infinity. So that works out. And then here, the 1 over x, as x goes to 0, let's put 0 here, 1 over 0 is also infinity. So this is going to be of the form infinity over infinity, which makes us nervous to write, but I'm just writing the form. So I'm writing it, you could say, in a formal way. I'm not evaluating that. I'm just writing that this is the form, infinity over infinity, which can be summarized like this. In any case, the theorem does apply. And you can take your limit as x goes to 0 from the right, and then you take a derivative here. The derivative is going to be 1 over x. And the derivative here is going to be negative 1 over x squared. Now, I'm taking the derivatives just straight up because I'm assuming that at this point you know how to take your derivatives. But if you have issues with this one you have to write as x to the negative 1. Where do I put it? Let's put it here. And if you take your derivative of that, you'll be dropping the negative 1 and then doing x to the negative 1 minus 1, so negative 2. And that's what I'm writing here, negative 1 over x squared, which is the same thing. Now, dividing by negative 1 over x squared is the same as multiplying times its reciprocal, as we said just a second ago. Seems like deja vu. So it's going to be 1 over x, and then times the reciprocal of this one, which is just reversing or flipping, if you will. You're a fraction, very technical I am. And then you just cancel. And when you cancel that, you can take your limit because there's no 0 in the denominator. So this is going to be the limit as x goes to 0 from the right of just negative x, which is just going to be 0 at the end of the day. So you were able to compute this limit. Yet again, you would have not been able to do anything algebraically there. So L'Hopital's rule came in to save the day. All right, so that's going to be another type of limit of the form infinity over infinity. Let's do one more example, and I think that at that point we can wrap up this video. All right, so let's close the video with this one. So let's evaluate, let's do the aside here. So at x equals to 1, what do I have? Well, I have x minus 1, which is going to be 1 minus 1, that's 0, times the tangent of pi over 2. You see? I wrote it twice and I wrote it wrong. I want a 2 here. Otherwise, pi over 4, then that's just 0. That's not fun. Direct evaluation gives you the limit. Who wants that? Let's do 1 at pi over 2. If I would have had pi over 4, by the way, if I evaluate it, I get 1 minus 1 is 0 times tangent of pi over 4, which is 1. 1 times 0 is 0. Nothing to do. You don't need L'Hopital's. You need nothing. Direct evaluation gives it to you. But here, with pi over 2, it's interesting because if you remember, so this is 0, and if you remember the graph of the tangent, it has 2 vertical asymptotes. One at, well, has infinitely many, but between negative pi over 2, you have 2 vertical asymptotes there. And so at pi over 2, I suppose I should also be doing the limit as x goes to 1 from the left, just to grab this side. You see, your function is going to be going out to positive infinity. So I have a limit of the form 0 times infinity. All All right, so last time, so we wanted either 0 over 0 or infinity over infinity. And this is neither. But, as I said last time, you can always convert a 0 times infinity into infinity over infinity by multiplying times the dividing by the reciprocal of the product, or the factor here you have. So you have this factor. Instead of multiplying times that factor, you're going to divide by its reciprocal. And now this term is going to go to positive or negative infinity as x goes to 1 from the left. What is this extra one? To negative 1? There, sorry about that. And then this one right here, the tangent of pi over 2x, is going to be going to positive infinity. So now you have it in this form, infinity over infinity. So you just transformed it, and now you can take your derivatives. So you go ahead and say limit as x goes to 1 from the left. Now the tangent, the derivative of the tangent is the secant squared. But you have to remember that chain rule tells you that you have to multiply then times the derivative of the inside, which happens to be pi over 2. That is just the derivative of the inside. And now here we're going to do 1 over x minus 1 squared, negative of that. That's the derivative of this one right here. All right, and now you're going to go ahead and evaluate. All right, so looking back at this situation, now if you take the derivative here again, you're going to end up with 2 secant times tangent, and so it's going to be 2 secant squared times tangent. You're going to still have an asymptote there. So what we're going to do is remember that our secant is 1 over the cosine. So we're going to use that, and we're going to reorganize this expression before we do another L'Hopital's. So pi over 2, I'm going to write this one as 1 over the cosine squared of pi over 2x. Now I should have put the x there. It looks ugly. And I'm going to leave this one alone for a minute. But now notice that I have this weird situation. I'm going to multiply times the reciprocal. So I'm going to put my negative, take it out, put the pi over 2 out, and write my limit, taking out constants to make things look a little bit better. And I'm going to do the reciprocal here. I'm going to write as x minus 1 squared over cosine squared pi over 2x. All right, so now when I evaluate directly, again, when I evaluate at 1, I'm going to have 1 minus 1, 0, and then cosine of pi over 2 is still going to be 0. So I have 0 over 0. Now I'm going to take another limit. So taking the derivative here, I get this. Taking the derivative here, I get 2 cosine squared, sorry about that, 2 cosine, not square, you take down the cosine there, pi over 2x, so that's taking the derivative of the square, times the derivative of the cosine, which is going to be negative sine, times the derivative of the inside, another pi over 2 that is going to go here. This was getting a little bit ugly, but we'll get through it. Now notice that the 2 here will cancel with the 2. The pi is going to cancel with the pi. The 2 is going to cancel with the 2. This one is multiplying, this one is dividing. And the negative will cancel with the negative. And so a lot of cancellation happened, and this is going to become just the limit. Whoa. Limit as x goes to 1 from the left of x minus 1 over this expression here, which is going to be cosine of pi over 2x, and then sine of pi over 2x. Now, if you evaluate at x equals to 1, you get 0 over cosine of pi over 2 is 0 again times 1. So you're going to have 0 over 0 one more time. So you can do yet another L'Hopital's. Now this derivative here, limit as x goes to 1 on the left, from the left of derivative of x minus 1 is 1. Now this one right here, you could take the derivative using the product rule, or you can cheat. I'm going to cheat because it's getting too long for this problem. What I'm going to do, I'm going to rewrite that denominator as, remember this trigonometric identity, that the sine of 2 theta is equal to 2 sine of theta cosine theta. So I have sine of theta cosine theta, so this is just really 1/2 of the sine of pi x. And so that 1/2 gives me a 2 here. This becomes the sine of pi x. Oh, this was the sine of pi x. Sorry, I have to write it as the cosine. So the derivative is going to be the cosine of pi x times pi. That's the derivative. And when I evaluate the cosine at pi x, finally, I get something that is not equal to 0, because cosine at pi is going to be -1, and so this becomes -2 over pi. So quickly, I'm going to show you an easier way to solve the problem that I did on the light board. So it was the limit as x goes to 1 from the left of x minus 1, and then tangent of pi over 2 x. So the easier way to do it, which I didn't think at the time, was just to write it as limit as x goes to 1 of x minus 1, and then I'm going to write the tangent of pi over 2x as sine of pi over 2x over the cosine of pi over 2x. Now I'm going to notice here that whenever you evaluate your limit, you can break it, and this sine part, that as x goes to 1, this goes to the sine of pi over 2, which is 1. So I can simply write this as the limit as x goes to 1 from the left of x minus 1 over the cosine of pi over 2x. I guess the x was there. And then at this point, I just do my L'Hopital's rule, because if I evaluate at x equals to 1, I get 1 minus 1, 0. And here I get cosine of pi over 2, which is 0 as well. Taking your derivatives at the numerator and denominator, you get derivative of x minus 1 is 1. Derivative of cosine is going to be negative sine of pi over 2x times the derivative of the inside, so you can put a pi over 2 here. And then when you evaluate, the sine of pi over 2 gives you a 1, and that's going to give you negative pi over 2, 1 over pi over 2. The reciprocal of that, negative 2 over pi, which was way less complicated than what I did on the light board. However, I think the video on the light board is still instructive, that once you start doing L'Hopital's, you gotta be mindful that you cannot just keep doing L'Hopital's over and over, because at some point L'Hopital's is just gonna start making it more and more complicated. When you start hitting that loop of things getting more complicated, you either have to stop and do trigonometric identities like I did before, or you gotta reevaluate your argument and see if it's making sense. So I wanted to record that addendum to what I did on the light board, so you could see that things can be a little bit easier if you reevaluate them. So it's instructional in the sense that you can do it in several ways, and sometimes some ways will be much easier. Of course, I wrote this problem as I was there, kind of on the fly, and is what happens whenever you do things with a little bit of spontaneity, however you say that. Anyways, thank you for watching, and I'll see you in the next video.